Okay, good morning. So today we will have resistors in series and parallel. This is the strengthening module of our electricity module. And if you remember from our electricity module, we had Ohm's law, and then we already talked about what current is, what resistance is. So now we'll eventually slide into solving simple series and parallel circuits. But first, let's isolate the two resistors in series and parallel. So let's first get to the basics. So when we say there are two ways in connecting circuit elements. The first one is series and the second one is parallel. So when we say series connected elements, you can see it's from end to end. So it forms a straight path. So this is a very simple example. We can assume that this is R1, this is R2, and this is R3. For a parallel combination, it's quite different. Uh, it's actually, you can see from the figure itself that there's a distinction. This has nodes A and B, and even if I stretch it, for each circuit element, there's a path. Unlike in series circuit, you can see from this, it's just a single path. Here, you'll be creating a path for R1, a path for R2, and a path for R3. Okay. If you want to look further, this is just a very simple illustration. It says that if you move the finger along the wires from A to B, you won't be passing any junction, meaning it just goes straight. So if I click that, there you go. You can imagine that that finger, that flow, that movement there will be your current flow. But of course, that's another topic. For now, let's limit it to the uh, arrangement of the resistances because it's just a straight path. Okay. For parallel, it's different. If I point my finger or if I point this finger from A to B, it's not sure. It's not gonna go straight to B because it has choices. Will it go to this point? Will it go to this point or will it go to that point? So that's a very outstanding distinction of a series and parallel circuit. So let's take them individually. So what are resistors in series? So resistors in series, you can see there. Again, we just used the figure we had a while ago. So it's R1, R2, R3. Often we'll be connecting them to a voltage source. I'm sorry. So that will be, let's say let's call that V. So if we get another value, which is current, it says their same current flows through all resistors. Yes, that's true. So whatever current enters this point A will flow through R1, R2, and R3. We can actually just assign one current there, and that will be the total current of the circuit. For voltages, though, it's different because R1 may be different from R2, may be different from R3. Thus, the voltage drop across each resistance will be different also. So, voltage in a series connected circuit will be additive. So, from the voltage across AD will be V1 plus V2 plus V3. Okay, now we get them further. So knowing that V is equal to V1 plus V2 plus V3, we also assume that I is the same for all. So getting from Ohm's law, I times R1, I times R2, and I times R3. Those are the individual voltage drops. So we can also say that this is V1, V2, V3, and of course this is the total voltage. And dividing those circuit elements by I, we can say that's R1 plus R2 plus R3 because of the equivalent resistance. So, sorry, we can go back. You can safely say that the total resistance of resistors in series will just also be the sum. So that's R1, R2, R3. So that will be your formula. So it says there for any number of resistors in series, all you have to do is get the sum of those resistances. And one thing you have to check, if you want to check if your answer is correct, R equivalent is always greater than any of the Ri. For example, I have three resistances and I connect them in series. Let's go back to that figure. Let's assume that R1 is 5 ohms, R2 is 10 ohms, R3 is a 15 ohms. So that's 5, 10, 15. All you have to do is get the sum. So it's 5 plus 10, that's 15, plus another 15 is 30. It's just really additive. Okay. Should have questions at this point, you can jot them down, and then we will do the question and answer later during the Zoom conference. Okay. Now let's go to resistors and parallel. So how different is it? A while ago, a few slides back, I said that the distinction would be, of course, arrangement. The arrangement of R1, R2, R2, and R3 are not in a straight path. So there will be junctions, or sometimes they call them nodes. So we can uh, say add current, or have current flow. If current flows in this circuit, it will branch out to I1, I2, and I3. We're assuming this is not an ideal setup, that R1, R2, and R3 are unique, meaning they're not the same. So you can say that I total, this one, is equal to I1 plus I2 plus I3. Okay. For voltage, well, it's quite obvious in the circuit. For voltage, you can see that the voltage across all three combinations will be equal. So whatever V you have here will be the V at R3, will be the V at R2, will also be the V at R1. So we can say, excuse me, from formula that VAB, or V equivalent, is equal to V1 equals V2 equals V3. Thus, if we use our Ohm's law again, we know that I is I1 plus I2 plus I3. And from formula, you know that V is equal to IR. So I is equal to V over R1 plus V over R2 plus V over R3. And we replace the combination by a simple equivalent resistor to get the R equivalent. So there you go. Eventually you get a formula which is equal to 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Meaning, unlike in a series connected resistance combination, the sum here won't be the actual sum, but it's the reciprocal of the sum of the reciprocals, or it's just this formula. All you have to do is get the inverse or the reciprocals, and then do a little calculator manipulation, and you get R equivalent. If you go back, if you two modules ago we had capacitance, it's different. It's actually the opposite. For capacitances in series, it's like getting formulas for resistances in parallel and vice versa. For capacitance in parallel, it's actually the same formula we use for resistances in series. Okay. In a gist, oh, I'm sorry, we forgot that. It says there, therefore the total or the equivalent resistance for parallel combination will be this one. It's the sum of the reciprocals, also the inverse of the sum of the reciprocals. So it says there, to check if you're doing it right, your R equivalent or your total resistance should be less than any of the R's. Okay, that's always a checkpoint. Okay, we will see in the example if we can apply that. So to compare them, by comparison, this is series. So this will be how it look like. We have three resistors. So it says here, same current flows, additive for voltage, equivalent resistances R1 plus R2 plus R3. For parallel, it's different. This is how it looks like. We know that the voltage is the same across each resistor, and I is additive because an I would flow here, an I would flow here, then I would flow here. Therefore, the equivalent resistance is different. Okay, if you have questions, again, please jot them down and we will do them, or we will go to them during our question and answer over our Zoom call. So what if it's a combination? So here you go. I have two examples. This one will be a ladder combination. How would you get the total resistance? So I also have a separate video for this one where it will be putting values so that we can later on compare so that you can solve them on your own. So when we are given a ladder, for this example or for this demonstration, I will be using the same R's for all. So if this is 1 ohm, this is 1 and all. Let's just do it generic. Let's do it a value R. So how do you solve it? Where do you start? Usually, you start by, it's always from the outermost to the innermost, meaning from the outermost right side, my right, to the left. It depends on how you're viewing it. So this is from right to left. So all you have to do is simplify them step by step. So what you do, it says here, for this presentation or for this demonstration, what I did is for a new color, that indicates another equivalent resistance. And of course, that will be made of the original ones. So first, get that. That will be in series. Eventually, of course, that series connected resistance will become one branch. And of course, that would minimize this original to this one. So that becomes a parallel combination. If you move further, if that is already in parallel, then you can also say that for that new resistance here, those three are in series. Okay. Then let's simplify further. Those resistances in series will now become a parallel branch, and it's of course in parallel to this. And eventually, for the last step, you can see that that equivalent resistance now forms a series combination with the last two resistances. And there you go. Finally, to get the equivalent circuit, that will be it. Again, reviewing it. Okay, I'll do it again. Let's put them back. Where do you start? This was our original circuit. That was our ladder circuit. So first, take the outermost, as I've said, from my right to the left. So getting those three resistances, those are actually in series. Even if you imagine you cut them or you just chop them off, you can see that they form a straight line. So that's a series connected resistance. And then after doing them in series or after calculating them in series, you connect, that will be a parallel connected branch. Then that parallel connected branch will actually form a series combination at this point. And then after doing that in series, you can actually see that those two branches are in parallel, eventually getting the total equivalent or the equivalent resistance. That will be it. Okay, I hope that's clear. Okay, and I also want to have one more example here. It says here, calculate the equivalent resistance of this circuit below. Okay, so how do I do it? The technique is always simplify it. So always get those chunks, small chunks, or if there are small circuits or small combinations that you have to solve first, you do them first. So here you go. Let's start to analyze this one. What I did, okay, it says here identify the chunks. Okay, so first, this is a chunk. This is actually a chunk here. So the 8 ohms and the 8 ohms will be simplified to this. Okay, I'm doing it now. I pre-solved them. So, but later on, I will show you the solution. So that will be a chunk. So doing that, though 8 ohms is in parallel to 8 ohms. So that's actually a 4 ohm resistor there. So after doing that chunk, you can see that this is another small chunk, but this is now in series. So 6 plus 4 is actually a 10 ohm equivalent. There you go. Then after solving for that, you can identify that the two 10 ohm resistors now are in parallel, so you can get the total resistance. So let's show the computation. So 8 and 8, that will be 1 over 8 plus 1 over 8. And then inverse. So it's 1 over 8 plus 1 over 8 plus 2 over 8. You have to get the reciprocal. So R34 is actually 4 ohms. Okay. And then also, if that is a 4 ohm resistance, this is quite simple. This is in series, so all you have to do is add them. So that's 6 plus 4. That's 10 ohms. And then eventually, those two are now in parallel. So 10 over 10. I'm sorry, that's 10 ohms and 10 ohms in parallel. That's 1 over 10 plus 1 over 10. That's actually a 5 ohm resistance. So the total or the equivalent resistance for this combination is 5 ohms. There you go. And eventually, the total resistance for the whole thing, because there's a 5 ohms, that will be your equivalent for R1, 2, 3, 4. And then you have one, which is 3 ohms, and another one, which is 1 ohm. Just add them all up. That's 5 plus 3 plus 1. The total resistance of this circuit is 9 ohms. So if a problem would ask you to get the current over a certain resistor, then we can compute that. But of course, for today, let's isolate it to what we're doing. We are trying to analyze small series parallel circuits. So again, I'll review what I did. First, this was the original circuit. Identify the small chunks. The first small chunk is 8 in parallel to 8. So that's 1 over 8 plus 1 over 8. It's actually 1 over 4. Then get the inverse. That's 4 ohms. Also, and then after doing that, it's a 4 and then 6. That's 4 plus 6. That's now 10 ohms. Eventually, we go to a 10 ohm parallel combination. So that will be 1 over 10 plus 1 over 10, and then get the inverse. That's actually 5 ohms. And for the final circuit, you get a 5 ohms. This is R1, 2, 3, 4 plus 3 ohms plus 1 ohm. And that will be 9 ohms. Okay, so I'll stop at this point. So I hope you were able to jot down important points. I will have another problem later for the Zoom call so that you can strengthen what we learned from this presentation. The presentation, by the way, will be available later on your module 10, which is resistors in series and parallel. And then after, I'll give you enough time to go over it. And then please go to your Zoom invite and we'll have our Zoom call for question and answer. Okay, I hope this was helpful. And should I have questions, I will be glad. I will entertain them later during our Zoom call. Okay, so good morning, and I'll see you later. Bye bye.